All right, so the reason why we do any of this is so we can apply, right? So we're going to talk about vector forces and apply. Okay, so just some applications of vectors. There's a lot. Now, a lot of these terms you might be thinking, oh, shoot, I haven't taken physics, or maybe you're excited because you've taken physics. But yeah, vectors have a lot to do with physics. We'll talk about them a little bit here. We can use vectors to represent displacement. We can use vectors to represent velocity, acceleration, and force. The unit is usually in newtons, although it can also be in pounds. But you'll see it in both probably. So let's say we have vector addition in one dimension. So as you guys can see here in this picture about the plane velocity and wind velocity, again, this is in one direction. When they point in the same direction, we can just add them, just like we would any two numbers. So the plane velocity was 100 kilometers per hour. The wind velocity was 25 kilometers per hour. So their resultant velocity in the same direction was 125 kilometers per hour. Pretty easy. Now, let's say that they go in opposite directions. So, like, you could think of like, going upstream, right? So, here's another example. It says, when vectors point in opposite directions, we actually subtract them, just like we would any two numbers. So, here's the plane velocity. The wind's going against the plane. So, the resultant velocity would be 75 kilometers per hour. Note, and this is true always, and especially in any application problem, you always want to check for units. You always want to make sure that the same units when these scenarios exist, because sometimes you'll be given different ones to just challenge you more. Okay, so obviously they're not always going to go in the same direction. They're not always going to go in opposite directions. It's possible for them to go in, different directions. So here we're going to add some perpendicular vectors. So we have a plane velocity of 100 kilometers per hour. We have a wind velocity of 25 kilometers per hour. So we would want to know how to figure out the resultant velocity. Now note that these two, if let's say I call this Vy, just since it's vertical, let's say I call this Vx. So these are our components to make the resultant vector, which we could call Vy plus Vx, right? Now, we actually, to find this resultant vector, because the vectors are at right angles to each other, in other words, perpendicular, we actually can use the Pythagorean theorem to find this, right? So I could actually do 100 squared plus 25 squared to figure out what this r squared is. Okay? So we could actually do that to figure out what that is. If they had asked you, like, what angle theta is, right? We would just use what we've been doing. The tangent of theta equals b over a, right? Now, this right here, we do need a little bit more context to actually, like, do anything with this. Like here, we think that this is going south. We think that this is going west. The magnitude of the vectors would actually be representing speed, which is what we're given here, right? So that actually represents the magnitude, which makes sense that this vector r, well, I guess it's not really r, but this resultant vector, we actually did find its magnitude because that's the speed, right? So that makes sense. But, in applications, the word magnitude is going to be whatever the units of the context of the problem is. So in this scenario, the units were kilometers per hour. Now, like I was saying, we need more context to this quote-unquote problem. Is the plane actually going south? We don't know. Is theta, the actual angle for direction of the plane? What quadrant is it in? What's the reference angle? Like, there's a lot that we don't know just because this is pretty broad. But just something to keep in mind. Look for your Pythagorean theorem. Okay, so vector components here. You're going to see some examples, especially in your problem set where you're asked to find the component vectors. So this is how you would do it. We can take two vectors and replace them with a single vector that has the same effect. This is called vector addition. We've done that. We can start with a single vector and think of it as a resultant of two perpendicular vectors called components. This process is called vector resolution. That sounds so formal. Okay, so this visual might help us understand a little bit better. So for vector resolution, we're going to be using right triangle trig, okay? Notice here that these vectors are all representing velocity. Remember how I talked about that vectors have a lot of applications. Velocity is one of them. So this is the resultant vector, this v equals 50 meters per second. Let's say we were asked to find its component vectors, which you can see here, it ends up being that the horizontal component is 25 meters per second and the vertical component is 43. But how would we get that? Right? It's kind of like working backwards. How do you work backwards from knowing the resultant? So to do that, well, we know that this angle is 60. We're told that. We need to know that. To find our horizontal component, we can use cosine, right? So cosine of 60 is just going to be whatever that vector is divided by v, right? So in this case, if I rearrange and solve, this v we know is 50. We can figure out what the cosine of 60 is. This will get us that our horizontal component is 25 meters per second. Likewise, if I was looking for my vertical component, or I would do the same thing. I know that sine of 60 degrees is going to be opposite over hypotenuse, so vy over v, right? So if I rearrange and solve for vy, I want my vertical component. That's just v times sine of 60. Again, we know that v is 50. We can figure out sine of 60. So our vertical component is 43 meters per second. So that's how we could get the components from working backwards using right triangle trig. Okay, so here's an example. You guys can totally do this using what we just talked about. It says we're walking a dog. Look at the cute doggy. Yeah. Okay. You're walking a dog and the leash is making a 40-degree angle with the dog's back. What a great posture, buddy. Okay. And you're holding it with a force of 60 newtons. Let's make this a little bit better. Okay. So your force, this is the leash, obviously, right? So it's the force or tension on the leash. This is V. That's 60 newtons. Okay. Okay. Just want to write that down. So we're asked to find the components. So you're essentially going to do what we just did above. So go ahead, put me on pause and try it out. So let's take a look here. Pretty simple. I already had it solved for the variable that I was looking for here. But the vertical component is 38.567 newtons and the horizontal component was 45.963 newtons. Okay. All right. So next example here. This one's going to be a bit of a doozy. Don't be mad at me. Okay. But we want to find the angle, emphasis on angle, between the forces given the magnitude of their resultant. Okay, so we have that force 1 is 3,000 pounds, force 2 is 1,000 pounds, and the resultant is 3,750 pounds. Okay, so as a hint for you guys, we're not given any direction for the forces. So in order for these to be force 1, force 2, and R, the resultant, there must be a specific angle between F1 and force 1 and force 2. However, that doesn't mean that they have to have specific locations. So to make it easier, I would intentionally choose force 1 to be on the positive side of the x-axis. Okay? You can do that. That's your choice. But what do I mean by that? I mean, so if this is force 1, like I said, I would choose that to be on the positive side of the x-axis. So, like that. okay? Your second force, you know, we don't know the angle between them, right? So like, if this was my other force, theta, well, remember that you can always rearrange it. You can always move them. And then like this would be oops, I want it to be a different color. This would be my resultant, okay? So they have a fixed relationship to each other, but it's not in a fixed space. You know, they have to be going relatively the same direction, since the resultant is larger than either the force individually. I can see that numerically, right? So they'd have to be going kind of in the same direction, force 1 and force 2. Okay, so maybe this picture or diagram is helpful for you guys. I would recommend using variables like x, y, and x plus y to represent these guys, x, y, and x plus y. And see what you can do. Again, we are asked to find the angle between the forces, this theta, okay? So go ahead and put me on pause. Again, we're trying to find the angle theta between force 1 and force 2. Okay, we know that their resultant is 3750 pounds. So I got my final answer that the angle between the forces is 47.384 degrees. How the heck did I get that? Okay, well, remember I gave you the advice to make this first force on the positive side of the x-axis. You are allowed to do that. So x is 3000 I, right? Because we know that the angle would be 0, right? There's no y component. For y, that's going to be 1000 because that's the magnitude. Cosine theta I plus sine theta j, which I just distributed the 1000. So when I find my rectangular form for x plus y, I add these two together. Okay? We don't know what theta is. That's what we need to find. We knew that theta for the x component was 0. Okay, so we don't know anything about x plus y other than that its magnitude is 3750 pounds, right? So if I actually find its magnitude, and you're like, oh my god, are you freaking kidding? And I'm like, yeah, it's okay, you can do it, right? We know that we can set that magnitude equal to 3,750. So we do that. Start by squaring both sides, right? That's how we can get rid of the root. I know these are large numbers, but totally doable here. Also, if you're not listening, you're just copying down my work, you're totally not going to know what's happening, so that would be a shame for you. Let's get rid of that red line. Oops. Get rid of the red line. Get rid of the red line. Okay, good. All right, so square both sides. Now I notice here that these terms have cosine squared of theta and sine squared of theta, and their leading coefficient is 1,000,000 each. So if I factor out 1,000,000 and I'm left with cosine squared of theta, sine squared of theta, that would just be 1. Now, this allows me to isolate cosine of theta, so I kind of skipped some steps, but you can figure it out. Cosine of theta equals 0.6771. Use the inverse cosine, and I get that the angle is 43 degrees about. All right, last example here. So we have forces, there's a little picture here, with magnitudes of 125 newtons and 300 newtons, and they're acting on a hook. So here's the hook. It's not a question mark. Now, the angle between the forces is 45 degrees. We know that much. Yay! Okay? We want to know the direction and the magnitude of the resultant vector. Okay? You guys can do this. This is totally doable. That'll be the 125 newtons. This can be the 300 newtons. Okay? So, go ahead, put me on pause, and then we'll check our work. Talk really fast because I'm going to run out of time. So I can find my trig form for x. I can find my trig form for y. Okay, knowing that the angles that they're at. Okay, I can find my trig form for x plus y. Now don't forget that to add vectors, oops, I would really be moving this guy over here, right? Head to tail. And then that would have a resulting vector, which would have a new angle theta, which is what we're asked to find. So I got that the magnitude was 398.319 newtons. To find theta, remember it's just b over a. I'm using that for the resultant vector. So I get that it's about 12.821 degrees. So that's my final answer. Again, I apologize, I'm going really fast, but I only get 15 minutes, so I'm making the most of every single second.